Hi, it's Alwyn. Let me tell you a story about accretion. What is accretion? If we think of the words accumulate, accrue, it comes from the Latin word that means towards or to or on. If we think of crescendo, crescent, and create, all things that involve growing, it comes from the Latin word, no surprise, that means to grow. Accretion is when one substance moves towards, to, on another substance, making it grow. In astronomy, many things accrete. Many things come together under the force of gravity to become bigger things, forming stars, planets, etc. At the same time, things that already exist, like black holes, white dwarfs, or neutron stars, can be made to grow by accreting gas. How does this happen? Perhaps at first it seems obvious. Gravity, which is ubiquitous in astronomy and the universe, pulls all things to all other things. And so of course things should come together, and accretion should just be an obvious result of existence. But let's think about the conservation of energy. When a ball falls towards the Earth, potential energy becomes kinetic energy. Potential energy decreases as the ball falls, and its speed increases and kinetic energy increases. Only when a ball collides with the Earth does the kinetic energy become heat energy, and the ball is left sitting on the Earth with less potential energy than before, and also zero kinetic energy because it's at rest. So far, no problem. Things can get closer together, balls fall onto Earths, they speed up, but finally they slow down and they rest together. But in space, when one thing falls towards another thing, the story is more complicated. When one thing falls towards another thing in space, it speeds up. But as it speeds up, it might approach escape velocity and end up being too fast to be captured. Potential energy becomes kinetic energy, but then can return to being potential energy if it turns around and slingshots away. For example, a satellite moving around a planet. You can imagine it slingshots away. A ball we drop on Earth has the benefit that it's guaranteed to collide with the Earth, which slows it down, but in space, things need a little help. Let's think about the conservation of angular momentum. Angular momentum is the momentum of things spinning around other things. It's what keeps things spinning. For example, tops keep spinning, ice skaters keep spinning, the Earth keeps orbiting the Sun, and the Moon keeps orbiting the Earth. And without friction or something like that to slow it all down, this continues on and on. Even though gravity pulls between the Sun and the Earth and the Moon, the orbits more or less don't change. A year is still a year, a month is still a month. The distance between the Sun and the Earth, or the Earth and the Moon, change only very slowly. So even though there is gravity in the equation, it's not the full story. Gravity alone does not cause the Earth to accrete into the Sun or the Moon to accrete into the Earth. Actually, through tides, the Earth is slinging the Moon away from itself by 4 centimeters a year. The Moon pulls the ocean tides back, and the ocean tides pull the Moon forward, causing the Moon to actually gain angular momentum and energy, causing the Moon to sling away from the Earth. You might have heard that a black hole sucks in everything, but it's not the full story. The gravity of the black hole is insufficient to suck things in. If the Sun turned into a black hole with the exact same mass, we wouldn't be sucked into it because we're too far away. Sure, life on Earth would eventually die off without the help of sunlight, but we would not be sucked in to a black hole if a black hole replaced our Sun instantly. Gravity is not enough to cause accretion. One thing is in common between conservation of energy and conservation of angular momentum. In both cases, because they are both conservations, we need some kind of collisions or friction to break the conservation, to turn energy into heat, and to slow down the spinning so things can just drop. Nature's favorite way, and my favorite way to do this, is the accretion disk. When a bunch of gas is around a massive dense object like a black hole or neutron star or white dwarf, it all tries to fall in at once. As a result, the gas collides with itself like a crowd of people trying to get through a narrow door. At the same time, due to the conservation of angular momentum, if the gas misses the object by a little bit, it spins around the central object. But since there's gas coming in from all sorts of different directions, they all collide with each other. In the end, things that don't collide along the same direction, things that don't spin along the same direction collide, leaving everything in the end spinning in one direction. Then we have an accretion disk, everything spinning together in unison. Gas moves almost circularly around the center, but it slowly spirals in. As gas slowly falls inward toward the center of gravity, it speeds up. Potential energy is turned into kinetic energy, just like how things fall on Earth or how roller coasters get faster on the way down. Thus, the gas further in is moving faster than the gas further out, and there's some friction as faster gas slips past slower gas. The friction takes just enough energy from the gas to prevent it from ever escaping, turning energy into heat so it can never be turned back into potential energy. It also makes sure that the gas loses just a little bit of its angular momentum, slowing it down, taking a bit of its ability to spin, preventing it from making a complete, perfect circular orbit, and instead it has a little bit less spin, causing it to spiral inward, just a little bit. Eventually, a particle of gas makes its way all the way down to the central object. Whether it's a planet, white dwarf, neutron star, or black hole, the gas moves towards the central object and makes it more massive. It adds itself to the central object. It accretes. To summarize, the accretion disk is what happens when you combine gravity with friction to allow things to fall in, but preventing them from speeding up enough to escape back out. Now the cool thing is, a lot of energy is released in accretion disks. Gas falls, turning potential energy into kinetic energy, and friction turns kinetic energy into heat energy, so it can never return to being potential energy. But where does all this heat energy go? The gas becomes hot. The hot gas does a few things. For one, as gas gets hotter, the particles inside are jiggling faster and faster. Collisions between atoms become so brutal that they knock electrons off the atoms, turning the gas into a plasma, protons and electrons whizzing about. Charged particles moving extremely fast in a chaotic, energetic soup release electromagnetic waves, the result of accelerating charged particles. This appears as light, and this process is what makes accretion disks the most powerful engines for producing light in the universe. In our galaxy, accretion disks are the reason for X-ray binaries and cataclysmic variables. Billions of light years away, accretion disks produce gamma-ray bursts, active galactic nuclei, and quasars thousands of times brighter than our entire Milky Way. Things so bright that we can see them even though they lie across the universe. I won't go into detail about these extreme astronomical objects, but hope these names pique your curiosity. Thank you very much.